You've been looking ahead and studying other stuff. This is brand new, and there are some subtleties here that will absolutely trip you up if you decide, nah, I don't want to pay attention. I figured out that nobody can really make you do anything you don't want to do, so I guess I can more or less make you be quiet, but if you don't want to pay attention, that's kind of your business, and we'll just let your grade be what it's going to be, and you will not get any extra sympathy from me. I'll just say, darn, you probably should have worked at that a little bit more. Anyways, I think this is really interesting. There's going to be some conundrums that show up here where you're maybe going to say, what? How is that possible? We'll see if those come up. So these, our topic here for today and Wednesday is not about rude integrals. It's not about, impolite integrals. That's not what the word improper means, right? Haha. No, not even a courtesy laugh from Nick. I am super upset about that. Improper. We're not talking about a lack of manners here, right? An improper integral is a definite integral where one or both of the limits is infinity, or you've got some kind of a continuity or discontinuity issue revolving around probably a vertical asymptote somewhere within your interval. These are called improper integrals. And why is that such a big deal? If you were to go back and look way back in Unit 2, and if you were to kind of dig through your book a little bit, you'd find out that the only way we can handle a definite integral is if the graph of the integrand is continuous on the interval that you're integrating on. And when we start talking about infinity, well, now infinity stretches out how far exactly, right? So we're talking about discontinuities and infinitely long intervals of integration. It doesn't fit the exact definition of what a definite integral should be. So we have our ways to get around that, namely this right here, limits. Limits will help us skirt our way nicely around the requirement that the limits be real and the graph have no discontinuities at all. Okay? So the limits are super duper important. Sometimes when we calculate these, we will get a nice, lovely real answer like 10 or negative 3 or 4 pi plus 7 over 13 or some actual real answer. Other times, you won't get a real answer. You'll get infinity or perhaps negative infinity. And we'll start to use this term right here, diverge. So we would say that the integral or the limit of the definite integral diverges to a non-real answer, probably going to be infinity or negative infinity. Okay, so just some examples of things that we can do with this. If I had some function, we'll call it f of x, and let's say I had a graph of f of x here, and let's say f of x had a vertical asymptote at 3, and let's say that the graph looked like this, right here. So vertical asymptote at 3, horizontal asymptote on the x-axis. Does that make sense? So here are some of the things we could do with this. We could be asked to find the integral from 4 to infinity of f of x. This would be improper because one of your two limits is not real, right? It's infinite. You could also be asked to find the integral from, say, 1 to 3 of f of x. So this is improper for a different reason. Why would this be improper? Yeah, so the right boundary is a vertical asymptote. So we can't actually get to 3, right? We're going to be getting real close to it, but not actually right there at it. Here's another example, integral from 1 to 5 of f of x dx. Same reasoning, right? As the other one. It's improper because of the vertical asymptote. Here's another one. We could handle this one eventually. Integral from negative infinity to infinity of f of x dx. This one's really improper, isn't it? Both the limits infinite, and you've got the vertical asymptote right there in the middle of your interval. So this one would be super duper improper. We'd have to do a little extra work for something like that. Does that make sense? Question?
The two in the middle, are those like
They are. They are because if you look at your limits of integration here, the 1 and the 3, do you see how the 3 is a vertical asymptote? So you've got an infinite discontinuity at 3. So if you think, if I'm going to integrate from 1 to 3, I'm essentially saying, let's calculate the area between the x-axis and the curve from 1 to 3. So we'd be talking about this area. Oh, Sam, so sorry. We're talking about this red area that I'm trying to highlight here.
Does f of x have to be a certain type of function?
Well, it's often, no, not really. I mean, this one I would say is probably rational because we got that vertical asymptote going on in there. But it could be exponential. Let me give you an example of that. So here's a classic example. What if I had, I'll give you a specific one here. What if I said g of x equals e to the negative x? I don't think I have this in our samples, so hopefully I'm not letting the cat out of the bag here. Too bad. Wouldn't this graph look something like this? It would go right there through 0, 1, and then it would continue on like so. That is one of the better exponential graphs I've ever drawn by hand. I'm really pleased with that one.
Solid.
Thanks, Sam. I tried, and it turned out okay this time. Okay, so this one could be improper or proper depending how it's set up. So if I said integral from, I don't know, negative 1 to 4 of g of x dx, this would be clearly proper or improper?
Proper.
So from negative 1 to 4, do you see any vertical asymptotes? Or one of the two limits, or either one of them or both of them infinite? No, so I agree. This is a very proper integral. It perfectly fits the conditions for a definite integral. But if I were to go, well, maybe I should ask you guys this. What would be a good example of how this could turn into an improper integral?
Negative infinity to 4.
All right, integral from negative infinity to 4 of g of x dx. That would clearly be improper, right? So now we're talking about from the far left edge of the graph, beyond that even, right? As far to the left as you could go, and then even past that up to 4. Well, one of the limits is not a real number, right? It's negative infinity. What would be another way we could write this that would make it improper?
Negative 1 to infinity of g of x.
Sure. Any real number, negative 1 fits that, of course, of g of x dx. Clearly improper again because of the infinity. So your question earlier, Forrest, was does it have to be a certain type of function? Not really. It could be rational, so you have a vertical asymptote like you see there on the left, or it could just be an exponential or a logarithm, or it could be anything, depending on what we were trying to find. Okay. Any other questions there? So the question is going to come up here at some point or another. Like let's say we took that last one, integral from 1 to infinity. Now again, isn't that essentially asking what is the area between the purple graph and the x-axis from 1 way out there to the right edge? I mean, this would just keep going and going, the area, wouldn't it? So what's the natural question here? What would you guess is going to happen?
It's going to be infinite.
You're going to ask the question, how could the answer not be that every time, right? Yet up here I told you something about sometimes these will converge to an actual real answer. So sometimes not infinity, but sometimes yes, infinity. How's that going to happen? That's what we're going to explore. Okay? So let's try to look for patterns, and you all can ask questions. And at some point between today and Wednesday, I'll start to help you see some patterns if you're not already seeing them. So we'll just kind of see how it all goes. So here is our first example, and I thought I would do this one with you just so I can show you some things that are expected. We can get some good habits started. I suppose the first thing we would look at and want to notice is that this is an improper integral. What's your first hint that this is improper?
Infinity.
Yeah, it's right there. The top limit is infinity. This has to be an improper integral. So here is kind of the first thing you really ought to do, and this is going to be kind of your doorway to showing that you know what you're doing with these and could get credit and get a good answer and all that stuff. Once you recognize this, you need to write limit as something. I often write the letter B, but it could be anything besides x. Limit is b goes towards infinity of the integral from 1 to b And I'd probably rewrite my integrand to look something like that. The key there is that you've got to treat the improper integrals with limits. So if you're going to do an improper integral and you never write lim, we got a problem. We got a problem. So let's start right there. So far, so good? To be honest, Nick, go ahead.
Are you gonna the limit from b to infinity be substituted?
We're not going to do that right now because then we're going to be back in the same place we were before. Remember, we can't handle these if one of the limits or both of them are infinite. And so this is my way to say, oh, look, it's not infinite anymore. It's just b. And then we're going to do all of our stuff with the antiderivative and the b and all that junk. And then at the very end, we'll say, well, what if b was heading towards infinity? What would happen? That's our way to get around this. Does that make sense? Okay. Anybody else? Okay, so a lot of these middle steps are going to feel really familiar because it's what we've done a lot of. So we're going to say the antiderivative of x to the negative 2 is negative x to the negative 1. We're going to evaluate that from 1 to b. We still have that limit hanging out there on the front, like so. And since we're doing a definite integral, wouldn't we then use the fundamental theorem and plug in the b and plug in the 1 and subtract, right? So hopefully, again, this is a familiar feeling step. Limit as b goes towards infinity of negative b to the negative 1 minus the negative of 1 to the negative 1. A lot of negatives. You just want to be super careful that you don't lose one of them. And then I'd clean this up a little bit and I'd say the limit as b goes towards infinity. And I could write, I suppose, negative 1 over b. You guys okay if I just write it like this? Negative 1 over b plus 1? Okay, so far what I've done is I have basically ignored the fact that this was an improper integral. I put the b in there for the upper limit and put this limit out there to signify that eventually I will apply this limit. And now it's time. So what would you guys say as you actually evaluate this limit? What do you get? 1. 0 plus 1, aka 1. So my final answer here would be that original integral from 1 to infinity 1 over x squared dx is 1. So who knew, right? I mean, the expected... Do you guys know what a graph of this looks like?
It looks just like the thing you did earlier.
It really does. It looks very similar, except it's centered at 0, right? So, yeah, this graph comes from the left and from the right. Looks like a volcano or something like that. So here is x equals 1. So what I did by calculating this integral, didn't we essentially find the area between the orange graph and the x-axis? We found that red area. We found out that it was not infinity this time. It was actually 1. So sometimes you will get actual real answers for these.
It kind of makes sense because the area is, even though, like, never mind. I was going to say, like, it's in a finite space, but that's not exactly true.
Yeah, because that orange graph never actually touches the
Yeah.
x-axis. It gets very, very, very close. It never actually touches it. Any other thoughts or questions on this one? If not, the next one might cause you to doubt. I don't know. We'll see.
I feel great.
Good. Yeah, question, Aiden.
So should we do like what we did with the last one where we did like therefore the limit from 1 to infinity equal to x squared dx?
I think that's fair. I don't think that we really have to do that because we haven't, like, I feel like with L'Hopital's rule, like we did the derivative of the top and the derivative of the bottom, and it's like it's this whole different looking function in the top and the bottom, and so I think it's important to tie it back around. But here we never really changed much of anything. I mean, we put the b in there and made the limit as b goes to infinity on the front. If you wanted to say therefore and say what you said, I got no problem with that. That's fantastic. But here it's almost like we just have this flow of thought leading to an answer. So, yeah, I could go either way on that one. Yeah. Anybody else? All right. So then why don't you guys try the next one? Number 2, it's on the next page. And you'll probably notice that it looks very similar. So this would be a good one to practice with and see what happens. Since you already saw this one and kind of worked through it already, maybe number 2 would be a good one for you to try on your own. We might not get it all sorted out yet, but hopefully we will. Hey, the idea that this is improper is pretty obvious, right? The top limit again is infinity. So we'd start off with that familiar look of limit as b goes towards infinity times of the integral from 1 to b of 1 over x dx, and then we get rolling with all the steps we know. So I would say the antiderivative is natural log of absolute value of x, evaluated from 1 to b, and we're applying the limit as b goes to infinity of that. So that'd keep going. I'd say limit as b goes towards infinity of ln of b minus ln, absolute value of 1 is just 1. So this would be where you could simplify things a little bit right away. What's the natural log of 1?
0.
So why not just do that and say limit as b goes towards infinity of natural log of b? This is where we would come to a conclusion. Do y'all know what the graph of natural log looks like?
Goes towards infinity.
It does. It does. So if I'll erase this in a second, but the graph would go through 1, 0. And it's certainly true that natural log does want to flatten out the further to the right you go, but it does continue to increase over time. It never actually flattens out or turns around. So as we think about what this limit would be, we're heading towards infinity, aren't we? We're not heading towards some nice number like 1. Or you could say something like this. Diverges. That would be a new vocabulary word that we'll start to use a lot throughout the year. So we'd say diverging because we got infinity when we applied this limit, right? So this might be worth talking about because a lot of you kind of looked at this a little bit weird and said, wait a minute, why did number 1, which looked really similar to this number 2, why did we get 1 for number 1, but for number 2 we get a very different answer? Doesn't exist, infinity, diverges. You can all tell the difference, right? One of them was 1 over x squared, and the other one was 1 over x, right?
When you look at the graph, it doesn't make any sense.
Well, when you look at I don't know, because you look at the graph, here is a graph in blue. This is 1 over x, right here in blue. And I'll try to be really precise with this. In red, you would actually have this. And I just graphed first quadrant there. Second quadrant would. They are very similar, but I very purposefully drew in the first quadrant the red graph the way that I did. It was not random. Let me ask you this. Where would this intersection point be when x equals 1, right? 1 over x squared, and x is 1, they're the same. So that's our intersection point. And notice as you move to the right, so as I move this way, isn't this an indicator that we're heading towards infinity? Mm-hmm. Notice how the red graph is a little bit below the blue graph. And you could prove this with a table on your calculator. Let's do it mentally. So let's think of numbers to the right of 1, like 2, 3, 4, 5, 6. Actually, let's not do it mentally. Let's do it up here. We'll just make a little table. You guys can do the arithmetic yourself.
1 over t squared is 1/4.
Okay, so when x is 1, 2, 3, 4, 5, 6, wouldn't 1 over x just be 1 over whatever? Like, it would be 1, 1/2, 1/3, 1/4, 1/5, 1/6. You can see that these numbers in this 1 over x column, they are heading towards 0, are they not?
Yeah. They sure are.
As x goes towards infinity, the outputs are heading towards 0. 1 over x squared, a little bit different. This would obviously be a 1. That's your intersection point. But what about when you plug in a 2? What would you get? 1/4. Keep going.
116, 125, 136, 149.
Etc., right? You're right. And in every single case, do you see how given the same x value on this domain, aren't the orange numbers less than or equal to the black numbers? So, we're gonna work on tying this up a little bit neater as we go throughout our year. But for now, here's what I'm going to say. Whether one of these improper integrals converges or diverges is going to depend on two things. Number one, are the terms heading towards 0, right? Because if the terms aren't heading towards 0, it's just going to be automatic diverge, right? Number two, not only do the terms have to head towards 0, number two, it depends on how fast they're heading towards 0. How quickly is it happening? Is it happening fast enough? Well, then maybe you'll get a real answer like we did in number 1. Is it happening too slowly? Perhaps like in number 2, it's happening too slowly, you get diverging, aka infinity doesn't exist. Okay? So it depends on how fast are we heading towards 0. Sam?
For number 2, can we just say that it diverges? Do we have to say that equals infinity?
I'd say those are all equivalent answers.
So we could just look at it and figure out whether it's
Sure.
goes.
And don't you have to have a pretty decent knowledge of what the graph of ln of x looks like to even do that? You'd say, oh, it keeps going up. So diverges or infinity, or you could say doesn't exist. I want to start steering you towards the diverges terminology because we'll use that more and more throughout the year.
We should do x cubed.
Oh, we should.
What does divergence
Pretty sure it equals the
mean
exact same.
technically?
Diverges?
Yeah. What does
It means that the answer is infinite.
But why do we say divergence?
Because it
So-
diverges from the reality. He's like, not at all.
We're heading towards what we're depending on how far we get into this, you're going to start to get a glimpse of power series, which you've already seen a little bit of. And so the deal with power series is that power series are supposed to approximate a function, the graph of a function. And as long as, if you have a graph, so let's say you have a graph that does this, right here, and you have a power series that's supposed to approximate it. So why don't I just do the board instead of hand motion? So here's your function of who knows what it is, but it's some function. You might find that your power series comes in and seems to really follow this for a while,
And it diverges.
but then goes away. It diverges from the path of the function. That's why we use that terminology, because we want it to actually perfectly mimic our parent function, but it could be that it does that for only a short interval, could do it for the whole interval, right? Or it could be like this, where it goes for a little while like we want, and then it diverges, heading towards infinity in this case, or negative infinity, away from what we think it should or what we want it to do.
But we won't really get to that until the power series.
Yeah, so I'm just trying to introduce that terminology to you,
Got it.
so that when we see that, you're like, okay, yeah, we've talked about this before.
So why does the rate at which it decreases matter so much? Because it won't, if we go to infinity, they'll become infinitely small.
If we go towards...
So if sorry, you're right, I did use a lot of programs. I still don't understand why, the difference between 1 over x and 1 over x squared makes such a large difference, and because you talked about how fast
Yep.
it grew smaller, right?
Yeah, how fast? Because they're both
So what, but
both
how
heading
do you-
towards 0, right?
Yeah. So if we scale that towards infinity, then why won't it map? I'm just confused. Why does that rate, or how fast it's decreasing,
right.
matter so much? And then is there any way, or is there any way to tell, or you just?
So if you're dealing with a rational function, and we're talking about an interval, say from 1 to infinity, then you're going to find that 1 over x, specifically that function, is the boundary between those that do and don't those that do and don't converge, or get a real answer.
Okay.
You're going to find that, again, given the parameters of integral from real number to infinity, and you got a rational function like that, you're going to find that if the exponent on the x is bigger than 1, you're always going to get a real number answer. And if it's less than or equal to 1, you're always going to get a non-real diverging answer. I feel like you're wanting to go deeper and deeper with that.
Yeah.
And I don't want to go there yet because we're going to do that in power series, and we need to kind of build to that. So that's why I'm saying, for the moment, I want you to think, okay, is this graph approaching fast enough, or is it not fast enough? Approaching 0 fast enough. So that's kind of where I want to land for the moment. We'll get into a lot of details later. We're going to talk. You guys remember geometric series from pre-calc? Geometric, like when it's 2 to the n,
Oh,
That's the
1/2 to the n, stuff like that, right? So we'll get into geometric series. We'll get into all kinds of different series and series tests to get into those details about what do we mean by, what exactly are we talking about when we say fast enough or too slow?
yeah, okay, fair enough.
So we'll parse that out later. That's okay. It's a great question. I get it, because it's you're just starting to see this, and you're like, whoa, what makes the difference? Yeah, I get it. Okay, so I would say that number 3 is one of my very favorite examples of the whole year. I love number 3. And I would say with some minimal calculator help, go ahead and use a calculator if you want to see what the graph looks like, and maybe a few other little details that might arise. But please try to find the area between the x-axis and the graph of that function, okay? Well, look at the graph. Look at the graph and decide, is that the real boundary? And here, I just asked area between the x-axis and that graph. I'm not going to do the whole thing right this second, but let's at least agree on this.
Arctan gives you an angle.
So here's the x, the y-axis.
It's the giant angle on the top, and then it's the giant side on top, and the really small side on the bottom.
Hey guys, hey, listen up. You guys all okay with this being the graph?
Yes, it's very cute.
That?
Okay, so then when I say find the area between the x-axis and that graph, are we not talking about all, oops, I want this right here. We're talking about all of this. So how far to the left would we have to stretch out in order to capture all the area?
I just kind of did it.
Negative infinity. And how far would we have to stretch to the right? Yeah, all the way to positive infinity. So,
not 10.
not 10.
Close.
10 is fairly close to infinity. So I think your original setup should be something like integral from negative infinity to infinity of 1 over x squared plus 1 dx. That would be where I would start. Obviously, there's long ways to go at that point, but that'd be where I'd start.
It is Arc 10. Oh my goodness.
Yeah, I think we all arrived at that conclusion like 5 minutes.
There's an arc 10. Well, if he hadn't stuck with his 10 so long, we'd be okay.
I'm sure we were all there.
10s.
I think it equals 0. That's my opinion, and I'm sticking to it.
Does that agree with what you're seeing on the graph, though?
Yes.
I don't think so. Because you only have positive accumulation all the way across that orange region.
I don't know what arctan of infinity is.
Got it.
The limit is
Okay, we'll get there. Well, so let's see what we can do here. We got to do the limit as b heads towards infinity of integral from negative b to b. That work? This would be one way to do it. Of 1 over x squared plus 1 dx. And as was just mentioned, you do have to figure out that the antiderivative of 1 over x squared plus 1 is indeed arctangent of x. So I'd go limit as b approaches infinity of arctan of x evaluated from negative b to b.
I figured it out. I'm really happy about it.
And then don't you have to come over here and say limit as b goes towards infinity of arctan of b minus arctan of negative b?
You got me there. So what do you do now?
So what do you do now? So it comes down to how do you evaluate the limit of arctan? And this might be where understanding what the graph of arctan looks like would be extremely useful. So I'm going to sketch it out over here. So arctangent, so this is a graph of arctan of x. And so here it is. It's got some horizontal tangents. It's got lots of them. And inside here it looks an awful lot like a tangent just tipped over on its side, doesn't it? Okay, so then as we say the limit as b goes towards infinity of either arctan of positive b or negative b, aren't we talking about the far right edge and the far left edge? So it comes down to what are the locations of those horizontal asymptotes? Do you know?
Pi over 2 and negative pi over 2.
Pi over 2 and... Hang on. Hey, don't ruin this moment with your, do we have to know this for the test? Tired old question. So,
What about the quiz?
shh, just stop talking right now. So would you guys be okay with the limit as b goes towards infinity of arctan of b? Wouldn't this just be pi over 2?
Yes.
Minus, what about the limit going to the far left edge?
Negative pi over 2.
Heading towards negative pi over 2. What is pi over 2 minus negative pi over 2?
Pi.
It is pi. I love this answer. Because if somebody were to ask you, what is pi? You'd probably be tempted to say, well, it's this number that's involved in the area of a circle. Or it's how the circumference relates to the diameter of a circle. Or something along those lines. Pi r squared, pi d, 2 pi r.
Integral of a hill.
Everything, yeah, exactly. So everything you would talk about would have to do with a circle this, a circle that, blah, blah, blah. When we first started off, I want you to think about this. We didn't start off with anything even resembling a circle, did we? No. Nothing about this looked like a circle. In fact, still nothing does look like a circle. And then we found the area, between the orange graph and the x-axis, and we went through all of our steps. We got arctan, and eventually we came around to pi. It's kind of a fascinating result. Because if somebody were, think about this. What if someone were to ask you, hey, I saw you writing this pi thing down. What is that? And you're like, oh, what's the integral from negative infinity to infinity of 1 over 1 plus x squared dx? You have no idea what you're talking about. And you wouldn't have, an hour ago, you wouldn't have known what that was talking about either. But now you do. It's a different way of calculating pi. Have you ever heard of somebody saying, I memorized the first 10,000 digits of pi? I've memorized the first 100 digits of pi and whatever, right? 3.141596162, That's about as far as I know. I personally think it's an impressive memory feat, but it serves almost no purpose because you have computers to do this for you. Have you ever wondered about this? When a calculator or a computer or whatever it is calculating out to the 10 millionth digit of pi or the whatever millionth digit of pi, what in the world is that computer doing? Is it...
It's adding up rectangles.
Oh, yeah, kind of. Is it looking at a bunch of different circles and diameters and doing a bunch of division and averaging it all out? No. You want to know what it's doing? It's using a power series to approximate this and just adding another term. Doesn't this seem like something that would be well suited for a computer?
Yeah.
Add a billion terms. Like no human is going to sit down and say, great, let's do that. They're going to say, well, maybe we could train a machine to do this for us, right? Because it can do it really, really fast. That's what it's doing. It's calculating this power series way out to the who knows where, coming up with like the 20 billionth digit of pi or however far they want to go, and it just keeps adding another term on. Again, well suited for a computer or a calculator to do, not for a human, not so much. That's where it's getting it from. That's how we would know something like this. So maybe a new definition of pi. Useful. If you want to memorize 10 billion digits of pi, perhaps. Okay. Unexpected answer? I think it's cool. Have any questions?
Another way to think about it is if you don't want to look at the graph, you just look at a triangle and ask if the opposite is infinity, because that's what it would have to be. Over, it stops over adjacent. If it's arctan,
Oh, I
it
see.
has
Yeah,
to
okay,
be
sure.
a giant number over a really small number.
Up to here,
What does that
right?
have to be? It has to be pi over 2.
Sure. Yeah, makes sense. Makes sense. Santi, did you have something?
Why are the limits pi over 2 and negative pi over 2? That's just like is.
Okay.
So when we try to evaluate this limit right here, just this first part, because we're applying the limit to both terms, right? So as I say, the limit is b goes towards infinity of arctan of b. We're basically saying what's happening on the far right edge of the graph. So like as x gets bigger and bigger and bigger, 100, a million, a billion, a trillion, whatever. We're going to the far right edge of the graph. A limit is asking you what is the pattern of the y values as x does its thing. In this case, going towards infinity. And we would say that the y values of our arctan graph are getting closer and closer to pi over 2 because of the horizontal asymptote.
I'm just curious, like, how do you know it's pi over 2? It's just like,
I'm a total math nerd.
Like, would you expect us to know that?
Yes.
Or could we look at a graph and just figure it out?
What about a triangle?
You could think about the unit circle triangle thing for sure. I don't know, like, do you know what the graph of just tangent looks like?
It's just
It's
like
like
a
that.
U kind of. Like,
It's not a U, it's one of these guys right here.
I like it.
or, yeah,
And it's got vertical asymptotes. Where are those vertical asymptotes located?
every 0 pi.
Every pi starting at like negative pi over 2, right?
Right.
Oh.
And we basically, remember how inverse functions are just reflections across the line y equals x? So if I were to graph tangent on top of this in a lovely, I'll go with green, wouldn't tangent look something like this? Can you see how that's reflected across the line y equals x, more or less? I mean, my drawing is not perfect, but it's close. So I would hope that if you knew the graph of tangent, you'd be able to say, oh, the graph of arctangent is just the double fold of that. So, yeah. Okay. Let's do one more. Example 4. Let's do this one together, though. So this might leave you in a slightly dissatisfied place. I'm okay with that, though.
It's going to leave us with a real number.
Why on earth is this improper?
Can't divide from 0.
The function isn't continuous at x equals 0.
What do we have at x equals 0?
Asymptote.
Vertical asymptote, actually. Vertical asymptote. So
Because
this,
it's on the bottom.
yep. So this graph would look something like this. It'd be 1 over x cubed, like so. And this is asking us to find the integral from 0 to 2. So 0 to 2, we'll just say that that's 2 right there. So we're trying to find this green area, and the green area bumps up against a vertical asymptote right there on the y-axis. So would you guys be okay if we just started off with limit as b approaches 0
Sure.
of integral from b to 2 of x to the negative 3? Right, I'm gonna always replace the limit that's got the issue, or limits that have the issues with the b. And technically it should be the limit as b approaches 0 from the right, because all of our y values are to the right of 0, or all of our x values are to the right of 0.
If we didn't put that, whatever.
And it's really not the end of the world, but appropriately it should be there. Okay, so then we run through all the steps we've done before. We find our antiderivative. So it would be, what, negative 1/2 x to the negative 2. Evaluator from b to 2. And then I go with all the other same kind of steps that we've always done. I'll plug in the 2. What's negative 1/2 times 2 to the negative 2?
Isn't it -1/2 times 1?
Negative 1/2 times 1/4. Yep, so negative 1/8. Okay, so negative 1/8 minus negative 1/2 b to the negative 2. Why what?
Why is it 0 positive?
Because you're approaching 0 from the right. All of our x's are to the right of 0. It's not going to really function. So the reason why we didn't have that on before is because we were approaching infinity. and you can't approach infinity from the other direction,
That'd be pretty cool.
right? You can only approach it from the appropriate logical direction. So we don't ever really put that on there. We could, I suppose. Okay, so then as I try to apply this limit, this is where we're going to come up with our final conclusion. It might be useful to go negative 1/8 plus, wouldn't this just be 1 over 2b squared? So as I try to apply this limit, what do I get?
Infinity.
Yeah, I would say this is infinity. This integral diverges.
Wait,
I don't like that.
As b heads towards 0, and the numerator is held constant,
What about the?
oh,
right?
What about the negative one?
oh, I get
Oh,
it. I-
wait.
What's negative 1/8 plus
Oh.
infinity?
Yeah, I see.
It's just infinity,
I
right?
don't like that.
That's not.
Wait, what? Wouldn't it be one?
Because B getting a bit small.
Very cool.
Keep getting smaller, so people want.
That's
Oh, wait, I get it.
that's awful.
I get it now, everyone.
You can look at a little table to see this. Would you guys agree with me that my b's are heading towards 0 from the right?
Yes.
Why did you?
So this would be 1 over 200th. This would be 1 over 2. But then we start to get large fast, right? So if I plug in 1/10, wouldn't I end up with 50, right? Yeah. And then I plug in 1/100th, that would be 1/10,000, that'd be 1/5, so I guess I'd get 5,000 right there. So do you see how these outputs are starting to get large fast, right? So once you get up to like 1 billionth, it would be what, 500 million or something like that. We're clearly heading towards infinity. And what's negative 1/8 going to do anyways? Not much. It's just going to be crushed by a steamroller of infinity. All right, thank you guys. We'll keep working on this next time.
Okay, well then better be on Thursday.